All right, welcome back to the second session of the day. This session is about interpreting machine learning, a topic near and dear to my heart. And by the way, I'm Adam Pear, faculty at Carnegie Mellon University, and I'll be chairing this session. And so we're going to kick things right off with a really interesting paper called Strategy Atlas, Strategy Analysis for Machine Learning Interpretability by Dennis Claris from Eindhoven. Oh, actually, sorry, just to remind you, we'll do questions on Slido, use Oklahoma 4, and then also, you can also come up to the mic as well. Sorry, Dennis, let's go ahead.
Do you ever find yourself questioning what a machine learning model is really doing? Hello everyone, my name is Dennis Claris, and together with Jack van Wijk, we hope to give you an insight into what these models do through our project Strategy Atlas. We developed this system in close collaboration with Achmea, which is a large insurance company in the Netherlands. So we've already conducted several studies at Achmea to help their data scientists understand and explain complex machine learning models. Explainable AI is particularly important for them, since insurance companies have to adhere to stringent regulations. The inspiration for this project came from one of the earlier projects that we conducted at the company, which was about fraud detection. The team asked that, in addition to explaining the predictions of a fraud model, whether I could tell them if the model found new types of frauds that were yet unknown to the experts. And this got me thinking, because this is not just a problem that's specific to fraud detection. In many cases, we build a model that predicts either class 1 or class 2, while in reality, a much more subtle class hierarchy exists. If a business like Achmea is predicting fraud, then they will typically label insurance policies as being either fraudulent or not, and then base the predictions around that. But there are, of course, many different ways how people can be committing fraud, even ones that are yet unknown. And in this case, the single model needs to account for all the different ways that fraud can occur, which leads it to become complex and uninterpretable. So in this project, our goal was to show whether or not a model has these different types of strategies to predict the same class, like we saw in the fraud example. To find these model strategies, we can start by just looking at patterns in the data by using dimensionality reduction techniques like T-Z-D or UMAP. Each point here represents a customer. Dark gray are predicted as good and light gray as bad. Now, some groups of similar customers do exist, but all clusters contain both good and bad customers. So it is still difficult to tell what the model is really doing here. So instead, we can try a projection that takes the model into account. So instead of data values, we use feature contributions for each data point. Feature contribution indicates how much each feature has contributed to the prediction for that point. And this is information that's specific to the complex model. In the resulting projection, clusters are again clearly visible, but now they neatly belong to either of the two predicted classes. And the clusters here mean that the model treats some customers differently than others. And this could indicate that the model is discriminating, for instance, based on gender or ethnicity, which is something we should definitely know. So we call this visualization the strategy map, as it highlights the presence of model strategies. However, in this strategy map, it still remains challenging to figure out what the clusters mean. What features are used for the classifications in a cluster? And on what grounds are data instances being treated differently? And does it even make sense for the model to make these distinctions? Well, to answer these questions, we introduce Strategy Atlas. The interface of Strategy Atlas offers 3 complementary views to support interpreting these clusters. There are gradient heat maps that enable the inspection of single features. Then there's interactive density plots that enable the analysis of clusters in terms of multiple features. And there's the cluster view that employs automated techniques to separate one cluster from the rest of the data and then explain it in terms of a decision tree. So the main interface components are also split into 2 rows. The top row shows components that show data aspects, whereas the bottom row pertains to only model-specific characteristics. We found that this is a very important distinction to make. So the first method to interpret these clusters are gradient heat maps. We again consider a 2-dimensional projection, and in this case we look at the training data. Each pixel in the background is now colored according to the interpolated feature value of each of the data points. And we use inverse distance weighting to achieve this. For example, here we can see that the points in the leftmost cluster all have a very low feature value compared to the rest of the data. And this is indicated by the light green background. And for feature contribution projections, we can apply the same trick. So in this strategy map, the background is colored according to the contribution of a feature. So in the blue regions, this feature has a positive impact on the predictions, and in the red regions, a negative impact. So heat maps are a particularly useful tool to focus on one specific feature. But if we want to be able to analyze many features at the same time, we include a second method through density plots. Each feature in the density, for each feature, the density is encoded like so. In gray, we see all data, and in blue, the currently selected points. And we can again apply this for feature contribution too. So here we can see how important the feature was for the entire dataset and within the selection. By default, the density of categorical features are encoded with bar charts like this, and numerical features are encoded with the line chart using kernel density estimation. This last encoding is particularly useful if we want to spot small differences between the distributions of the primary and the secondary selection. However, the encoding can be chosen in the interface at will. But how do we even make such a selection? Well, the main way to select points in the system is through lasso selection in the data map and the strategy map like so. However, it is also possible to brush the axes of the density plots. In addition to analyzing single clusters, the system enables the contrastive explanation of what a cluster means. We can select two clusters and then explore the differences between them. This is done by using the right mouse button for a red secondary selection. Anywhere in the system where a selection can be made, you can use the right mouse button to turn it into a secondary selection. In the case that we have many different features, it may still take a long while to scroll through this list of density plots. And hence, actually, the most important or most powerful feature of this view is the various sorting options that we included. You can sort feature values on standard deviation to see which features that data points have in common. You can sort on the contribution, or you can sort the contributions on mean value to see what are the most important features in a cluster. And you can sort by selection separation, which sorts the features based on the difference between the distribution of the selection and the rest of data. And to achieve this, we use Kolmogorov-Smirnov. So the last method to analyze strategy clusters is to train a simple decision tree as a surrogate for the complex model behavior. First, in this view, you can save and reselect clusters. And here you can also give the saved cluster a name for future reference. Next, pressing this button will train a decision tree that for each of the saved clusters that separates the point within the cluster from the rest of the data. Such a strategy tree provides a natural way of describing the most important decisions that the model made for such a cluster. And it is a familiar encoding for our target user, the data scientist. The ensemble of these strategy trees may actually provide a more interpretable alternative for the complex model that we started with. And for this purpose, the interface includes a brief performance comparison at the bottom. In this example, we show a set of strategy trees that achieves identical performance to the complex model, while is only 5% the size of the complex model. But this is not always the case, and for more information, we refer to the paper. For use cases, we recommend checking out our website, explaining.ml, where we host a video with a full walkthrough of the system in a use case on credit scoring. There, you can also find an online demo where you can try out the system for yourself. Next, our paper contains more details about another case study that we conducted at Achmea with an automatic acceptance model that was applied to a large portion of all the car insurances in the Netherlands. So, this concludes our presentation of Strategy Atlas, a visual analytics system designed to identify and interpret different model strategies. There are several directions for future work, some of which we actually already started addressing a little bit, such as addressing the scalability of computing feature contribution, in incorporating the inherent uncertainty associated with explanation techniques, and improving the faithfulness of our heat map visualizations. And with that, I'd like to thank you for your attention, and I'm open for questions.
All right, thank you, Dennis. And I will read some questions off Slido, but again, if you'd like to stand up and come to the mic, you're welcome to ask them live as well. Our first question is, did you find there were any kind of artifacts or limitations to kind of using post hoc techniques like LIME and then UMAP that might introduce some imperfections, and how did that affect kind of analyzing models, if so?
Thank you for that question. So yeah, this was one of the future works that we pointed out. So there's always some uncertainty associated with both the explanation technique and the projection technique. And as far as I'm aware, so if the UMAP projection or the explanation technique is not, if there are small differences within those projections, then we don't expect to see very clear clusters. So the strategy map really is most effective if these clusters are very, very visible, and that means that there's a large difference between the data points and large difference in the feature importance technique. So in those situations, that doesn't matter as much, but we really like to look into this uncertainty aspect more further.
Great, thank you. And time for one more quick question. Can you use the system for analyzing the training process in a dynamic way? And have you ever tried it on CNNs for image analysis?
Thank you for the question. So the system is fully model agnostic, so you can apply it to any model that you'd like. I think, but it is mainly built for tabular data. So CNNs could work, but then you need a CNN for tabular data, which is maybe not the best approach. So analyzing the training process in a dynamic way, I don't think the system will be very suitable for, because we use a post hoc technique. So we need the fully trained model in order to obtain the contribution factors.
Great. All right. Thank you. Well, sadly, we're out of time, so I encourage you to reach out to Dennis after the session or via Discord. So thank you all for listening. Okay. Thanks. Let's give another round of applause for Dennis. Thank you. Okay, our next presenter is Nangji from Ohio State University, and this is an exciting paper that won an honorable mention, so we can cheer for him after he gets set up, but I'll present him with his official certificates in just a second, but let's get his. And Ning will be talking about VDL surrogate, a view-dependent latent-based model for parameter space exploration of ensemble simulations. All right. Please.
Okay, thanks for the introduction. Hello, everyone. I'm Nengshi from the Ohio State University. I'm glad to present our work entitled VDL Surrogate, a view-dependent latent-based model for parameter space exploration of ensemble simulations. So actually, this work is about scientific simulations. As we all know, scientists usually run ensemble simulations given different input parameters to perform parameter space analysis. And here you can see, scientific visualization is always a very useful tool to help scientists explore the simulation output efficiently and intuitively. However, there's one problem remains, that is, the simulation space exploration usually requires us to exhausting the complicated parameter space by running a batch of computationally expensive simulations. So scientists want to deal with the question. To make the parameter space exploration more efficient, scientists would try to exploit surrogate models to mimic the original expensive simulation model. And existing surrogate model-based parameter space analysis in our visualization community usually are either data-based, such as our previous work NNVA, or image-based, such as our previous work InstruNet, which leads to their corresponding limitations. First, for this data-based method, it is usually very difficult for them to directly produce high-resolution simulation output. And second, for this image-based method, they usually first visualize the simulation output with several predefined visual mappings. So that leads to a problem. That is, scientists are not able to adjust the visual mappings after the model has been trained. So they cannot find features of interest very easily. So in this work, we are trying to propose a surrogate model solve these two limitations. We propose a surrogate model exploiting representations that are first, view-dependent latent, such that it can support visualizations of high-resolution simulation output. Second, not dependent on predefined visual mappings, so that the surrogate can support visualizations with different visual mappings. And in the next slide, I will further clarify the first point. That is why we want to use view-dependent latent representations. So as I mentioned before, the key of our work is to use view-dependent latent representations. First, I'm going to explain why a view-dependent strategy is necessary. Now imagine you have a very, very high resolution simulation output. At that time, you may not want to directly visualize it with its raw data resolution. Instead, you may want to produce an output with the desired image resolution, but focus on maintaining the quality of the simulation output along the view direction. And it's obvious that after applying this strategy, there would be some savings of our method. Second, I'm going to explain why we need latent instead of just applying the view-dependent approach alone. This is because if we use the view-dependent approach alone, the GPU memory constraint still does not allow us to train the surrogate model successfully. So we want to use the latent representations along the view directions to further improve the model efficiency. So let's start to present our method. To begin with, I would love to give you an overview. Note that the training phase of video surrogate is composed of two stages. The first one is called view-dependent latent generation, and the second one is called the video predictor training. And there are two major networks in the pipeline. The first one is called Ray autoencoder, abbreviated as RAE, and the second one is called view-dependent latent predictor, abbreviated as video predictor. Before diving into the details of the two training stages, note that our view-dependent latent representations are generated given a selected viewpoint. And in our work, we will select three view directions parallel to the three main axes and generate the corresponding view-dependent latent representations for each viewing direction. Okay, now let's dig into the details. This slide actually describes how to generate view-dependent latent representations that are later used for the downstream predictor training. And I would say the biggest benefit of this step is to help reduce the computation and memory cost of the downstream predictor training. And here's what we do. First, we have a full resolution simulation output. And given a viewing direction, we will consider to sample it via interpolation to obtain a view-dependent data. Next, with the view-dependent data, along the view directions, we will cast rays parallel to the view axis and collect the ray samples. Then the ray samples are encoded by the RE encoder to ray latent representations, and then decoded by the RE decoder to the reconstructed ray samples. For the details of the RE structure, please refer to our paper. Next, I'm going to describe the video predictor training phase. After an RE is trained, we will try to run more simulations and perform this view-dependent sampling on the simulation outputs. Now for this new generated view-dependent data, we will encode them with the trained RE encoder for latent representations. And now we have the pair of input simulation parameters and view-dependent latent representations. We can train a convolutional model called video predictor to learn their mapping. As well, for the details of the video predictor structure, please refer to our paper. In the inference stage, as illustrated, for a selected viewpoint, we will first feed the unseen input parameters to the trained video predictor to generate predicted view-dependent latent representations, which is then sent to the RE decoder and decoded back to the data space. So note that our final goal is to generate the visualization result from an abstract viewpoint, and we should have something to deal with it. Now look at the viewing sphere. For an abstract viewpoint V, we will cast rays to sample the three predicted view-dependent data generated from our previously selected viewpoints. And at one sample location, we will average all the 3 values sampled from the data by inverse viewpoint distance weighting, such as you can imagine, the sampled value from a closer viewpoint should contribute more than that from a more distant viewpoint. We validate our method using 2 simulation datasets for different scientific applications. In the following slide, I will mainly focus on qualitative evaluation and parameter space exploration case studies. For more results, please refer to our paper. So the first part is about qualitative evaluation. Okay, for our first dataset, NIX, which is a cosmology dataset, we predict visualization images of the log density field from a sequence of different viewpoints. Here you can see video surrogate would generate high-quality visualization images without popping effect when changing viewpoints, compared to the baseline method in StreetNet. And for our second dataset, MPass Ocean, we predict the visualization images of the temperature field from a sequence of different viewpoints. And we have similar observations. The next part is parameter space exploration. First, for the next dataset, we fix other simulation parameters and sample the simulation parameter Hubble constant h from 0.55 to 0.85. From the 2 images rendered with different transfer functions, we find that the high density region becomes smaller as the simulation parameter Hubble constant h increases. Second, for the MPass Ocean dataset, we fix other simulation parameters and sample the simulation parameter BWSA from 0 to 5. As shown in the left part, the sea level temperature map, when BWSA increases, the blue stripe in the image becomes more evident. And in the right part, from the visualized 3 isothermal surfaces, we can see that the surfaces have a higher curvature when BWSA increases. Talking about the performance, after training, forward pass through our trained video surrogate takes less than 1 minute, instead of the roughly 1 hour it would take to directly compute the simulation output on a large cluster of CPUs. In conclusion, we propose video surrogate, a view-dependent neural network latent-based surrogate model for parameter space exploration of ensemble simulations that allows high-resolution visualizations and user-specified visual mappings. We also demonstrate the effectiveness and efficiency of video surrogate by comprehensive quantitative and qualitative evaluations on cosmology and ocean ensemble simulation datasets. Thanks for listening. We also thank our funding providers. Now I can take some questions.
All right. Thank you for that great presentation. And we have quite a few questions on Slido. We'll try to get through a couple. So one says, for Marco, congratulations, amazing work. Did you consider using foveated rendering strategies for a view-dependent sampling process?
Currently, I would say no, because I only actually I mentioned in our work is I only select 3 viewpoints prior to my exit, and I would say from implementation is pretty easy. It's like in implementation you just squeeze the tensor, and I do not consider any fancy engines or like that. But I would say definitely I would consider that.
Sounds good. And then the last question we have is, so you need to keep 3 copies of the reduced data in your network, similar to the old slice-based volume rendering technique, using 3 stacks of slices. Is that optimal?
I would say because our main goal is for GPU memory, and if you do not do that, you probably need a very strong machine, and with that, you probably can it's like kind of distribute workload to different like GPUs. Yeah,
Makes
it's
sense.
our consideration.
Great. Wonderful. Let's thank him again and congratulate him on his honorable mention. Thank you.
Thank you.
Thank you. Okay. All right, next up, we have Jianming Wang, who's going to be talking about Concept Explainer, interactive explanation for deep neural networks from a concept perspective. And again, as you're listening to Jianbing's presentation, you can add some Slido questions to Oklahoma Station 4.
All right, so hello everyone. I'm Jingbin Huang. I'm currently a fourth year PhD student at Arizona State, and together with Aditi, BC, and Chris, we built up a system called Concept Explainer, which provides interactive explanations for deep neural networks from a concept perspective. As we all know, deep neural networks nowadays have achieved tremendous successes in many application scenarios, such as autonomous vehicle, medical, and image classification, which is one motivator scenario for our work. But it's frustrating sometimes when we try to get an intuitive explanation, but all we get in return is something that we can't totally make sense of. And the reason is because there's a mismatch between the level of expertise of the user and the specificity of the explanation. For example, the deep neural network developers with sufficient expertise might want something more detailed with neural architectural details revealed. The same amount of information can just easily overwhelm model users, someone like me who have technical background but don't necessarily have any experience in deep neural network development. Prior techniques that try to provide intuitive explanations actually try to just map back to the input features to figure out what object contribute to what predictions. But the problem here is they are oftentimes just localized to one instance, and they can't easily scale up to a large data set. To achieve high-level explanation that covers the entire data set, we need to incorporate what's called a concept explanation. And we can define a concept clearly as a set of hairstyles and texture images. And it's human understandable we can explain the model's behavior in terms of what concept influenced the model by how much. For example, we can define the wheel concept and the police logo concept and check out how much the wheel concept and police logo concept influence a police van class. Unfortunately, even though these advantages of concepts explanation, it hasn't been widely used mainly for three factors. First, concept explanations have been remaining broadly a manual process. Even if we can automate the generation process with a large data set, it will result in a massive concept space. So there's no trivial way to reveal useful insights to the users. And these challenges are actually what motivate us to build up our concept explainer to make concept explanation more beneficial and accessible to model users. To guide our design, we ran a pre-study and we identified 4 goals for our design that covers all levels of data granularities, and I'll walk you through them all. First, at the global level, we want to generate concepts automatically and structure the concept space so the user can easily navigate the space and make sense out of it. Going a level down at the class level, we want to see what are the influential concepts to a class. For example, the wheel concept is influential to the police van. For multiple classes, we want to also see how the overlap of class in terms of concepts. For example, both the police van and the fire truck has a wheel concept that's influencing them. And then to the finest level, we want to know how a single data point or an instance, and in our case, which is an image, will be influenced by concepts. So our build system following these goals and after iterations and prototyping, it finally looks like this. The system consists of a backend and a front end. The backend takes care of our first goal to generate and navigate the concept space. The front end takes care of the other 3 goals to provide interactive explanations. In the back end, we first discover concepts using the ACE method, and I'll refer you to our paper to check more details. And because we target real-world application scenarios, we picked a 22-layer Google Net that's trained on an ImageNet dataset with 1.2 million images and 1,000 classes. After discovering the concepts, we filter them and get rid of noisy ones and cluster them. The clustering also gives us a structure to more organizedly discovering the concept space. Finally, all the information is wrapped up in an interactive interface for model users so they can obtain useful insights. The system consists of mainly 3 parts. The user can either start from the right-hand side or the left-hand side to start their analysis. If the user starts from the left-hand side, they can browse the interesting classes that they want an explanation about. If they start from the right-hand side, they can browse interesting concepts and start from there. The central ground is where you can dig into details and to match concepts with classes and figure what concepts is influential to what classes. And now I'll demonstrate a use case scenario so you can understand how we can obtain insights from this system. We can start from the right-hand side and look at concept clusters with deeper color, which means these concepts inside this cluster are highly influential. However, on the cluster, we'll be able to access individual concepts within it. As we can see here, the selected cluster contains the stripe concept. And as we know, both the zebra class and lionfish class are influenced by the stripe concept, as we show here. So if we add these 2 classes to the central panel for investigation, we again can see that there's an overlap between each other by the stripe concept, and it's quite prominent. In fact, both the zebra and lionfish classes are highly influenced by the stripe concept, but they differ from each other from the desert concept and seawater concept. And if we checked out a failed instance where the network misclassified as a zebra as a llama, we can see that it's because probably the picture has no obvious stripes in it. And this way, we can see how the network understands a class. In addition to the demo scenario, we also have 2 more usage scenarios in our paper, and we also ran a user study to evaluate the usability of the system. And we found out there are a couple insights, and we want to highlight them here. The system was found to be useful for contextualizing concepts, revealing class-specific concepts, and inter-class conceptual overlap. And it is also found to be useful for identifying data quality issues such as mislabeling, and we also mentioned it in our paper. To wrap it up, Concept Explainer discovers high-level concepts in the backend, and it provides interactive explanations for deep neural networks using discovered concepts in the front end. And please feel free to read our paper for more details. With that, I will conclude my presentation. Thank you so much for listening, and I'm actively looking for a summer internship in 2023, so contact me later, and I'm happy to take questions.
All right, thank you, Jinbin. So again, if you have a question, feel free to come up. Otherwise, I'll start by kicking off some of the questions from Slido. So one of the questions is it often possible to assign a semantic meaning to the concepts that are automatically extracted?
Yeah, that's actually a good question. So that would be something I would mention as our next step of work. And we actually have a continuation of this work that we're trying to use vision language model to tag a concept. Right now, it's more perceived like when we see the concept, we understand what it means. But we're also using some deep learning method to try to provide a semantic meaning for them.
Makes sense, thank you. And another question comes from Vidya, which asks, does the interface support showing related clusters based on some common subset of properties in the concepts?
Can you say that question again?
Does the interface support showing related clusters based on some common subset of properties
of the concept?
Yeah.
Right now, we haven't thought of that yet because we try to sort of pull up everything together in this interface. So there's some features that we need to give up, and like showing common properties of concept might be another system. So we haven't added yet in our system.
Makes sense. And then we'll follow up with one last question, which for Fourier, who says, an image contains not only human understandable concepts, but also uninterpretable features. So I'm wondering to what degree a CNN model can be explained only with concepts. Do you have any findings of this from your user study?
Oh yeah, right. So concept is probably more for like, so in terms of like searching, you have breadth first and depth first, right? So to give a more fast check of what the neural network's doing, we can use concept. But for more detailed insight, we definitely need to open up the black box and show all the architectural details.
Yeah, great.
All
right. Well, unfortunately, we're out of time for questions, but there were a lot more, so I encourage you to follow up with them on Discord or chat with Jinbin after the session. So
Thank you so much.
go ahead. Thank you. All right. Our next presenter is Xiaoyu Zhang from UC Davis, and I want to award her and our fellow co-authors another Best Paper Honorable Mention. So congratulations on that. And today she'll be talking about Slice Teller. Thank you.
Hello, everybody. I'm Xiaoyu Zhang. I'm a PhD candidate from UC Davis. Today, I will present our honorable mention work, Slice Teller, a data slice-driven approach for machine learning model validation. This is a collaborative work between UC Davis and Bosch Research, and also my internship project with George Huan Liang Liu from Bosch Research and my advisor Kuang Lu from UC Davis. Let me start from an example of autonomous driving. In autonomous driving, it is necessary to achieve a certain model performance on critical objects for business acceptance. Models are required to meet product requirements under different conditions of weather, temperature, object types, and so on. For example, objects such as children and curbstone might be prioritized depending on the business. Such models also need to be analyzed in order to find and mitigate problematic slices, such as rain and cold weather. To tune the model for these conditions, we need to evaluate the model in these scenarios by slicing and dicing the data. So now you may ask, what are data slices? Data slices are human interpretable and actionable data subgroups identified with metadata. For example, the weather, distance, object types for the autonomous driving example. But the validation data, sometimes aggregate machine learning metrics can hide problems. For example, the validation dataset might have an overall accuracy of 0.99, but slices as object car and temperature high might have different data properties. These are the slices we need to pay extra attention to. Why? Data slices can lead to better evaluation, as they can highlight portions of the data where the model fails. For example, in the autonomous driving, we identify that scenes with sunny weather and high temperature can be more challenging. Furthermore, data slices can indicate problems during data acquisition. Let's look at another video-based example, fire detection from video. We identified that such detection in the outdoor scenario had a higher false positive rate. Upon data inspection, we found that this was due to label imbalance. That will guide us to collect higher quality training data in the future. However, it is challenging to identify and mitigate these model issues. The first challenge is problem discovery. In particular, how to evaluate the exponential search space of all possible data slices. The second challenge is model iteration. Training machine learning model can take many hours, which interrupts the experimental cycle. So how can we quickly iterate model without retraining? Our solution is Slice Teller, a data slice-driven model validation tool. We allow users to automatically find data slices, perform slice-based evaluation, what-if analysis, and finally, VA-assisted model improvements. Our framework starts from an automatic data slice finding process. Given a machine learning model, we test it on the validation dataset and apply a slice finding algorithm to automatically search for human interpretable slices that can be explored with our visual analytics approach in the next step. To achieve the automatic slice finding, we leverage the state-of-the-art slice finding algorithm and develop a pipeline to conduct the frequent item mining, metric computation, and redundancy pruning on the input dataset. After we collect the candidate problematic dataset, we input them into our slice-based VA interface, which supports the users to interactively explore the slides and identify the critical ones. The main component of our VA interface is slice matrix, a representation that summarizes problematic data slices. In the slice matrix, row represents data slices, and columns represents one-hot encoded slice description. Slice metrics are shown for every data slice. When users select a data slice, we also provide detailed view for future data inspection. Once critical data slices are identified, we use our novel slice boosting method to estimate the performance trade-off for prioritizing different slices. We input the selected critical slice into our original slice boosting algorithm for a what-if analysis. This slice boosting method leverages the residual of the predicted result on the validation dataset and trains a shallow regressor to minimize the prediction result. As a result, the system will show us the estimated effect of model optimization over the selected slice. Finally, we can iteratively optimize model over the critical data slices with different approaches, such as importance weighting, group optimization, and data augmentation. Now I will show 2 use cases of slice tailor for model validation and improvement. Let's start from a public dataset, Saliba, which consists of pictures of celebrity faces. We train a model to classify the hair color, gray or not gray. We use the metadata including 40 binary attribute annotations about the images. After we import our tool into the Jupyter Notebook and inspect the model with slice tailor, we notice a potential bias. As slide 1 indicates, the model is failing to classify females with gray hair because of a small dataset size. We can further verify this observation by browsing the sample images in the matrix view. Based on this observation, we decide to optimize the model over the biased slices with a group-based optimization method. After the optimization, the method's performance on the gray hair female is significantly improved, as well as other worse performance slices. As the second use case, let's revisit our autonomous driving example. In this case, we show how slice tailor can be used to improve perception models for autonomous driving. Our goal is to train a robust model to classify object heights with ultrasonic sensor data. We use a tabular dataset with 8 numerical or categorical annotations as metadata. First of all, we use slice tailor to investigate the problematic slice from the model. As we can see here, they include slice 1, sunny weather, high clutter, slice 2, high clutter, low speed, slice 7 and 10, curbstone, and container slide. The what-if estimation shows that when optimizing the selected slices, they will be improved. We retrain the model with model reweighting. We use the same parameters but more weights for the selected slices. This new method can indeed improve the slice performance. However, we also notice a trade-off on slice 139 and slice 142. We found the trade-off on slice 139 not acceptable because the rain condition is critical for autonomous driving. In the next iteration, we also optimize the model for the slice 139 and obtain a good trade-off across all slices. And now, we are successfully met the product requirements of the detectors at this testing stage. We can then pass the model for downstreaming tasks such as sensor fusion. To wrap up, we developed the first of the kind of thorough model validation tool that integrates a novel visual analytics tool, slice tailor, and an efficient algorithm, slice boosting. Our tool is generalizable and has shown the ability to penetrate many real-world business use cases, such as AI fairness, autonomous driving, and intelligent video analysis. That concludes my presentation today. Again, I'm Xiaoyu Zhang. I'm also actively searching for postdoc or faculty job position. If you are interested in our work or working with me, please feel free to reach out. Thank you for your attention.
Thank you, Xiaoyu. Great presentation.
Thank you.
Okay, we have a handful of questions here. Two of them are kind of related. Do you think it's possible to kind of automatically extract the labels for some of these slices based upon the metadata that's using them to create them from your slice finding algorithm?
That is a very good question. Actually, that is our future work and also the work we are working on at the moment. So we think it is possible. So although we have already closed the loop of this whole model validation process, we believe that we can do more, like automatically extract the labels, as you mentioned, and then incorporate that into our whole like model validation and improve loop. Yeah.
Great to hear. That will be an active research topic. Excellent. Another question is, cool work. I wonder, would it be possible to include data slices that are outside the distribution of the original data? So looking at robustness against unexpected input?
If I understand it correctly, that means, is it possible to identify data slices outside the regular metadata, or?
I guess so. If the author's in the room and wants to clarify.
Yeah, so I'm just thinking, like the robustness against unexpected input, like in your car example, if a unicorn crosses the road, we don't want the car to like flip around all of a sudden. So like looking at, so it's not necessarily a data slice then anymore because it's not a slice of the original data, but could this also be used in the case of like identifying unexpected?
That is a quite interesting question. So actually, currently our work is based on the metadata. So it is, if it is not identified in the metadata, probably our size finding algorithm will encounter some problem. But yeah, quite interesting. Probably when we develop our new tool to identify the labels for the data set, we can consider this. So the user can select which label they want and they can define what is outside, what is inside.
We have time for one more question. One is, do you have any sense of what are the limitations with regard to the number of metadata attributes? The number of slices could explode if you have lots and lots of attributes. So, yeah.
Yeah, that is also an interesting question. So actually for this work, we use like we mentioned, the state-of-the-art existing work to do the size finding, and we did encounter the problem that there is a exponential searching space, so sometimes it takes time. So we devised a like 2 iteration size finding, like we do like close like parameter searching for the first iteration, and after that we find better parameters. We can do the finer like granularity search. And that, according to our practice, significantly reduced the time we need to find slices we want.
Great, thank you. Okay, let's give another round of applause for Xiaoyu and her team. And again, congratulate her on her honorable mention paper and her colleagues. Thank you. Our next talk is by Peter Xenopoulos from New York University, and he's going to be talking about Calibrate, interactive analysis of probabilistic model output.
So, hello everyone. My name is Peter. I'm here today with my colleague Joao, who's sitting over there, and today what we're going to talk about is model calibration, why it's important, and what we do to address some issues in model calibration. So to begin, usually, let's just start with the machine learning process. So we start with our input. We feed our input into a model, and then our model outputs something. And it depends on your application. It could be a label, it could be a score, it could be a probability. Now, what we're concerned with here is when our model outputs a probability. And the question that calibration tries to get at is how well do these outputted probabilities align with the true outcomes? So when the model says 70%, does it actually occur 70% of the time? That's the question that we're talking about today. Now, predicted probabilities are useful for a very wide array of domains. So for example, in healthcare, in banking and finance, and even in criminal justice. But it's not simply that the probabilities are used in these fields. It's also that these probabilities are conveyed towards many downstream stakeholders. So let's consider a very simple scenario, which we're all familiar with, which is a meteorologist. They go onto the TV, they tell us what the chance of rain is. We take in that probability of it raining to influence what our dress decision is going to be for that day. But a little bit more seriously, we have economists that quantify recession risks. We have doctors communicating with their patients, which they may also quantify risk using probability. And it's very important that the probabilities that the models output that then get conveyed to end users, it's important these probabilities are calibrated. So the main tool that we have to analyze model calibration are reliability diagrams. And these are a very, at this point, old technique. They're a static visualization. And the way that they work is the following. You simply take your predictions, you bin them based on their probability. So in this particular case, we have 10 bins. These are the blue bars. And in each of these bins, you calculate what the true outcome rate is. And a perfectly calibrated model would follow this middle dotted line. But what we actually see is that particularly for many of the newest kinds of models that we think about, like, for example, many deep learning models, they can achieve high accuracy, yet they can actually be very miscalibrated. And this is, as I said, this is quite common, as you'll find with some of these newer modeling techniques. So calibration is actually quite an old topic. This is a table from 1920. This is a table that a meteorologist created. And this is the first attempt at reliability diagrams, but as you'll see, we have not really deviated that much since then. We fast forward 50 years, we get to this image, which this is the reliability diagram that we're quite familiar with. And then if we fast forward even more, we see that we haven't changed very much. We've added some gaps to illustrate the calibration error, but the general concept is the same. Now, reliability diagrams are very, very simple, but they're still very powerful. Despite all of this, there are a few things, few challenges that we would like to address. The first is that reliability diagrams rely on a few parameters, which we'll enumerate later, and very small changes in these parameters can actually lead us to different conclusions. The second thing is that because of the static nature, it's very hard to iterate and to investigate certain subsets of the data. Particularly if you're doing this in the Jupyter environment, you have to do all of this pandas legwork, and it can become very cumbersome. And then the last challenge is that the bins it's very opaque to the end user. We don't know which observations are necessarily in which bins, and it's hard for us to analyze those bins. So what we do is we make the following contributions. The first is we introduce learned reliability diagrams. This is actually just a simple tweak to the original reliability diagram, and this helps reduce some of the variability that we get with parameter selection. The second contribution is calibrate, which is an interactive system to analyze a model's calibration. And then we also introduce some case studies that use the LRDs and calibrate on criminal justice and synthetic data. We're going to cover the first two in this talk, but if you'd like to see the case studies, I encourage you to look at the paper. So we'll start with learned reliability diagrams. So the two main parameters that reliability diagrams take are the bins and then the strategy, which is simply how the bins are created. Here you see examples of different bin and strategy combinations, and you can see that we can end up with quite different interpretations, quite different appearances of the reliability diagram simply by changing the parameters. So a little bit more fine-grained here is we have an example of a model trained on the Wisconsin breast cancer data set. And we have two reliability diagrams, one with 8 bins, one with 10 bins. We simply changed the number of bins by 2. But what we would see is that this particular region, if we used 8 bins, we would say the model is well calibrated here. But if we use 10 bins, we would say, whoa, there is significant miscalibration here. So this is a simple example to show you that, particularly for these small to medium-sized data sets, the choice of bins and how you create those bins can have very significant effects on your interpretation of the model's calibration. So we address this problem in the following way. First, we observe that reliability diagrams are effectively trying to estimate the relationship between the predicted and the true outcomes, and they do so using binning. Now, we actually propose to learn this relationship rather than learn it by using bins. So what we say is this is actually just a simple process of taking the predictions and finding their relationship with the outcomes. So this is actually just a univariate function. We could learn this in any way that we think of using typical ML. So choices of F could include things like you could use splines. In our particular case, we use explainable boosting machines, but the choice of F is really left up to the user. And this is actually, we'll note this is similar to how one may fix their probabilities or calibrate their model in a post hoc fashion, except we have no restrictions on what this F may be. So I'll just give you an example here. On the right are the learned reliability diagrams, and you'll see that we can change the parameters all we want in the explaining boosting machine, but the general shape of the learned reliability diagram is quite stable, particularly for this small data set of the Wisconsin breast cancer data set. It's about, I believe, 500 to 600 samples. And so this helps stabilize what we would actually see in the reliability diagram. Now, the second contribution is calibrate, and this is actually what implements learned reliability diagrams along with some of these interactions that we mentioned earlier. So calibrate was developed in conjunction with some data scientists who routinely analyze their models for calibration. So calibrate is Jupyter first. It's meant to run in Jupyter notebooks, so we bring this to where the data scientists are actually doing their model analysis. And so a user will first create a calibrate object. They'll attach some data, some predictions, a model to it, and then to get started, they'll start creating these reliability diagrams. So they can select which class they're interested in, from which model, how many bins they would like to use, and then they can also create learned reliability diagrams on top of that. So all of this populates the reliability diagrams view, which is C here. And a user can select a particular line, and then that will populate the histogram underneath, which shows the predictions. And this will give a user a sense of where the reliability diagram may be less reliable than in other sections. This interface is also a user can actually drag and select certain regions of the data in the reliability diagram view, which will then populate the views D and E, the instance inspection, the performance metrics. And this will allow them to understand better what's happening in those regions, if there are particular characteristics of that region, perhaps there are certain features that pop out, and so on. And then the last component is the subset creation, this is very popular among data scientists, is they want to analyze how well calibrated their model is on different subsets. Because when reliability diagrams are typically created, they're done so on the whole data set. But that doesn't mean that certain subsets are miscalibrated. And all of those components that I listed are interactive. So if you'd like to use Calibrate, you can install it on pip. It's got a very simple interface to use, which you can check in our GitHub. And so I encourage you to visit these links if you're interested. And please reach out to me or Joao, talk to us at the conference if you'd like to learn more about Calibrate. Thank you.
Thank you, Peter. So again, feel free to post your questions in Slido in Oklahoma 4, but there are a handful of questions here as well. So the first question is there a way to automate the number of bins or strategies used for your reliability diagrams? Does this require user expertise, or does it not matter much with your kind of new contribution?
So Sorry, it was hard to hear the question.
Oh, sorry. So you mentioned that you need to kind of specify the number of bins and strategies used to kind of generate these reliability diagrams. And so the question I think was, does this require user expertise? Can it be automated? Or does it not really matter much given your kind of new contribution?
I would say a lot of this depends on the size of your data and also the type of model you use. In practice, what a lot of people do is they select 10 bins or 20 bins. If you have only 500 data points, if you select 20 bins, depending on how the distribution of the predictions looks, you could end up with very odd-looking reliability diagrams. So I think this is where the learned reliability diagrams come into play. That allows a user to not have to think about those types of decisions. They can simply create the learned reliability diagram, and it makes the process a little bit easier. But for larger data sets, typically you can get away with running a standard reliability diagram, maybe with 10 or 20 bins. It just depends on the data and the distribution of the predictions, more importantly.
Makes sense, thank you. We have time for one more question, and this is maybe a higher level question, but the question noticed that a few papers in the session kind of were implemented inside the Jupyter Notebook. And so I guess just a higher level question of, do you feel like this is an important direction for the Viz community to kind of go inside that environment?
I don't know if I'm qualified to answer that. I think that at least in our particular use case, and from what I've seen, working at least with people that work with calibration, is that a lot of times they may have a collection of models that they run in some sort of Jupyter notebook, and they may not necessarily be writing their predictions to a database. And it's much easier for them to have something in their Jupyter notebook that they can go and iterate in. So for example, here, this subset creation, they may find a certain subset that is not well calibrated. And I do a lot of work in sports betting, and we actually find things like, models are very poorly calibrated at the beginning of games. And so that's very helpful for thinking about features that we may want to engineer, or perhaps just telling us where we shouldn't use our model. But I think that it's very helpful to have these things in Jupyter.
Great. All right, let's thank Peter one more time. And our last paper of this session is by Zilan Yi, and he's going to be talking about visualizing ensemble predictions of music mood.
Hello, everyone. Today we are going to introduce our project about visualizing ensemble predictions of music mood. We started this research as music enthusiasts and machine learning model developer. We aim to understand and decode music using machine learning, but then we found that only the visualization of music can well address this problem. So we then converted into Viz. We visualized the ensemble machine learning results of music mood. We introduced the new visual design as a variant of the theme river, which is called the Duflux theme river. And we visualized the Bach Paritita 5 in G key. And now let me give you a brief introduction of about our work. And let's start it with some music. Well, music mood classification has been an important problem in terms of music understanding and machine learning. Music without lyrics could be even more challenging, as some of the moods are relatively vague and complicated, while providing more flexibility for listeners' understanding. In this segment, could it be calm or relaxing? It is really hard to say whether there is a clear mood in this segment based on different people's understanding. And more importantly, for machine learning, Traditional music annotations for music mood classification task usually label a piece of music of a certain length, let's say 30 seconds. This seems to be very inaccurate, as music usually can have a lot of changes of mood. Therefore, we conclude three main challenges to address this problem for the current music mood classification problem. First, as we know, the label of the current music mood dataset are the annotations for the whole piece of music. Such a long music segment only has one mood label. It is an over-abstraction of the music mood, and therefore the global label is not ground truth. We do need local label that can describe music more accurately. However, a very short music segment may not stand for anything really that makes sense to human, as it is simply too short, and the ground truth label are difficult to obtain. And secondly, as the previous example shows, the music mood is inherently uncertain. Some music gives relatively clear mood. And the others could give a rather complicated mood. The music mood can also be very subjective based on each individual's understanding. We do need to develop a method that can well collect and illustrate all the meaningful votes from different understanding. And thirdly, the traditional ensemble machine learning models give only one single prediction from many opinions. This over-abstraction also makes it more difficult to deliver complicated and uncertainty information for the two problems mentioned above, especially when majority vote method is used while two opinions are very close. On the other side, each single base model is trained with global labels. So to address these three challenges mentioned above, we firstly use a family of decision tree-based algorithms to collect as many opinions as we can. And as we know, Ensemble combines the votes from different machine learning models, and which is similar to opinion polling or voting for machine learning that changes from time to time. The algorithms we used includes bagging, AdaBoost, random forest, and etc. Here we use 7 different machine learning methods and 30 sets of features generated from music segments from different lengths, so from 1 to 30 seconds. And we generate 210 machine learning models. We use feature-based machine learning to classify about 900 pieces of music into 4 mood groups based on the widely used Russell's psychological model. However, the result is rather disappointing. The best result among individual models are just above 67%. We also tried various ensemble methods to adjust the weight of each model, while the best result achieved is just above 70%, which is only 3% above the best single model's performance. Although using ensemble learning only does not address all 3 challenges, we can still keep the result and visualize it. Therefore, to illustrate those local labels, uncertainty, information, and each model's vote, we introduced a very popular design called Theme River. And as we all know, Theme River is naturally suitable for time series data. Firstly, the moods from segments of each second are predicted and synchronized to give the predicted label for each second. This is therefore the local label generated from models. From the global labels, sorry. Secondly, we keep all the votes from 210 machine learning models. Some votes may be considered as noise, while the uncertainty and minority information is still preserved. And thirdly, as ensemble learning usually gives only one result, we kept all the votes and used visualization to show the general view. Well, in this way, music mood classification results are shown more precisely and much closer to the actual ground truth. However, with only the theme river, it seems very difficult to identify the dominant mood, the ordering, and the ordering change of the votes. We can only see the rough proportion of the votes from a mood, especially when two moods give similar votes. The cognitive cost could be very high to read the theme river. To reduce the cognitive cost, we introduced our new visual design, the Duflux theme river. Firstly, we put the dominant opinion on the top flux and put the remaining opinion at the lower flux in the descending order. In this case, we can easily identify which is the main mood along the music, and the ordering change can be detected very quickly. The ordering change of minor mood can also indicate some change in the chord progression, for example, the melody, and or even some change in the instruments or the arrangements. And secondly, we add a 50% threshold line, which indicates half of the votes, as the weights of votes are calculated based on the accuracy of each individual machine learning model. This 50% threshold line will not be a straight line. With this, we can easily identify the dominant opinion and whether it is above 50%. We can also observe the change of ordering as the music being played and synchronized it with the music score to observe why there is a mood change. This helps the understanding of music composing as well as providing a way of enabling expressive AI or the understanding of AI. In addition to that, we can use the Duflux theme river in conjunction with pixel-based visualization to firstly observe the individual model's performance, and secondly, compare groups of models with similar attributes. And thirdly, we can also obtain an effective overview for observing the performance of many models in the context of different music. In pixel-based visualization, each row represents a model, and each prediction stands for a prediction of 1 second. Therefore, there are 210 rows or models for each pixel-based visualization. The first column is the prediction results, and the second column is the class-based accuracy of each model. The third column is the overall accuracy for that model, and the color map is shown below. We combine the Duflux theme river and the pixel-based visualization to see each prediction from each model, and therefore it is easy to observe, for example, any patterns for models with similar attributes. Here we can see that the model of higher accuracy usually give more stable predictions, while the lower ones seem more random. And on the other hand, we can change the ordering of 210 models and grouping them by machine learning methods, time interval, or the combination. So let's see another example. So here we can sort the model differently, which is by methods and then interval length as shown on the left, or by the interval length and then accuracy as shown on the right. If we sort the model by methods and then interval length, we will easily find that most of the machine learning methods follow similar patterns, except the basic decision tree and the AdaBoost tree. These two methods give more random prediction, while the others show a decline of angry mood as the increase of the interval length. So if we sort the model by interval length and then the accuracy, it is very clear that almost all the angry moods comes from the models with shorter interval length, which may indicate that the models with shorter interval length could be more stable, could be more able to detect the angry mood in the first half of this piece of music. And therefore, as it is easy to change the sorting scheme, we will be able to find where each mood comes from in the Duflux theme river. So based on the previous experiment, we have conducted analytical evaluation, which is proposed by Ming Chen and Ebert. It involves symptom, cause, remedy, and side effect. We also did human-centered evaluation that includes common sense suggestions from 3 experts from both music and machine learning side. And in conclusion, we developed this new due flux theme river. We addressed the challenge and apply this for ensemble machine learning to enable more models and complicated analysis. From music perspective, this enables more complex classification with uncertainty, and this can also be generalized for any other similar applications with multiple data stream, like opinion pooling and emotion featured in text and videos. So for more information, please refer to the paper. Thank you very much for listening, and please do not hesitate if you have any questions.
Thank you. All right, we've time for one quick question. I guess this is maybe more of a clarification question, but it seemed like in the theme river, the sum of the 4 moods was not constant over time. Was that true? And if so, why was that?
I'm sorry, say again.
The sum of the 4 moods over time seem to not be the same in the theme or visualization.
Yeah.
Is that true? And if so, why?
I think it really depends on the music, and for example, some of the music in the Russell's group, they have a calm class, and I don't. There is no, from my perspective, there is no like stronger calm or just normal calm. So it might give very flat result in that case.
Makes sense. Okay, I'm sorry that's all the time we have for today, but thanks our speaker and all of our speakers for the session for wonderful presentations. Thank you all.